Okay, all good to go. Um, so hi, let's talk about what's on the agenda today and what I'm going to go through. I will review this paper, AIRL, which is like Adversarial Inverse Reinforcement Learning. Um, I will just go through the paper and what it talks about very quickly so that we'll have a recap and we understand what's going on here. Because later I'm going to use it for the codes. And this would be like 1 50-minute set, hopefully, not more. And for the next two sets, we will go through one IRL paper, that is a survey paper, and we will just read as much as possible. There's no rush to finishing it, but we will just go through it so that I can understand it better. And as our, like this would be like first half of the day, and as our next half of the day, I'm just gonna go through AIRL code, which is the same paper, but it's code-based thing, which is presented by Imitation. There's like a framework called Imitation on GitHub, and yeah, I think that's everything for today. And I hope that I can manage to do like 3 sets in here and 3 sets in here. And I'll talk about all of the science behind it so that we can grasp a better understanding, which would be helpful for me as well. So, yes, without further talk, maybe let's just start. I'll probably have to stop my mic just for a second, just to make sure that the whole streaming thing is working smoothly, and then we can start, probably in a minute. All right, everything sounds good and in place. So let's just start. I'm gonna set a timer for just 15 minutes so that we know when to stop. Okay, let's do this. All right, so the paper is called Learning Robust Rewards with Adversarial Inverse Reinforcement Learning. This is just another inverse reinforcement learning method. Now, as you recall, the whole idea behind inverse reinforcement learning was that, like, let me see if I can make a new note here. Yes. So the whole idea behind inverse reinforcement learning was the fact that we have a bunch of rewards. Um, that is hard to specify. So how can we get these rewards? We will grab a bunch of trajectories, which is like a combination of a state, action, next state, next action, etc., etc. And then these trajectories are available to us because there are experts who can do these trajectories for you and who can make these demonstrations for you, so you can use them. So the whole idea behind inverse reinforcement learning is that, okay, why not using these trajectories so that we know what was the reward behind it? So how can we use these trajectories so that we can find the rewards? Now, there are a bunch of challenges behind this whole idea, and the fact is that there are so many rewards that can describe a policy, and there are so many policies that can describe a reward. And that's like a problem here. So finding a good reward here is the challenge. Now, on the first step, there was this method called maximum entropy, IRL, for which the idea, like this was by Zibart et al. So the idea of maxent was that, okay, let's make the least assumption here in order to find out what was the reward and what is the expert trying to behave based on. So how can we make the least assumption here? No bias at all. Let's see what is the most random way that we can justify these trajectories that we are seeing. For that one, we made the rewards to be like a linear combination of some features that are defining the states, and then the rewards would be like some linear combination of these features. So it's like for every single state, you will just add these things, and that will be like your reward function. Maybe a summation would not be a good thing here. And after that, we have like a feature expectation, which is like if I have, let's say like there is a trajectory that is made by the expert and it goes through this specific states, and I'm just counting and like adding them up, and I take the mean over all of the trajectories. Like if I have m trajectories made by the expert, and if I take the mean, the uniform mean of what's going on in these trajectories and how many of the features are being used, I'll get a feature expectation, and I will try to build a policy that would match this feature expectation. I know it's a bit crowded, but I think this background was necessary in order to understand this whole idea of adversarial. So that's why I thought maybe it wouldn't be a bad idea to just share it here. All right. So we'll just go through the algorithm so that we can have a very, very short recap of the whole idea and what's happening here. So as a first part, first they talk about their related works, and maybe I just turn on the highlight so that we can go through some of the text here. So first they talk about their related works. They first talk what is IRL and what was the whole idea behind it, and then they mention Zibart's work, that they how he is using maximum entropy in order to remove the ambiguity between demonstrations and the expert policy, and allows us to cast the reward learning problem as a maximum likelihood problem. This is also a keyword here. And next way, they talk about their own method, that they say that their method is very close to Gale. Now, Gale is another method. Gale is for imitation learning. How Gale is doing is like, okay, what if we had, let's assume there is like a, hold on. Let's assume there is a policy generator, and then there is a discriminator, which is like a GAN framework. So the policy generator would generate a bunch of trajectories that are firstly coming very random, and then there is a discriminator that is trying to specify which one was coming from this generator and which one was coming from the expert. So if there is something coming from the expert, it will categorize it as expert, and if not, it will categorize it as a generator function. And the policy generator's goal is to make better and better trajectories to resemble experts so that it can fool the discriminator, so that the discriminator can make a mistake here and doesn't understand which trajectories are actually coming from the generator. Now, the whole thing here is that if you try to reach to a policy that is best representative of the expert, then you have basically reached to the imitation learning problem. So you are imitating your expert here. Why? Because you are making a policy that is imitating the expert. So you have learned what the expert is doing, and now you can use it for your own good. So if there's like a robot thing and you are trying to learn a specific thing from that robot, you can use this so that you can teach your robot that, okay, now we are trying to, let's say, take this glass up. So you are teaching your robot to do this. Now, what is different here is that when we are talking about imitation learning, your robot will learn to just imitate the expert, but it doesn't understand what was the reward here. So it will not infer what was the goal of the expert here. So maybe every time the expert goal is to put this glass of water on a table. Now, when you just learn the policy, if you change the glass of water or if you change the position of it, because the robot has learned just to mimic the expert, just to imitate it, it will not make a good like trajectory now that everything has changed. But when it knows the reward and when it knows that the goal is to put this glass of water on the table, even if the table is changed, even if the glass of water is changed or the positions are changed, the robot will still keep putting the glass of water on the table. That's why learning the rewards comes handy here. So they mentioned that their proposed method is very similar to Gale, and however, it differs from their work because Gale is not an IRL algorithm, so it's not trying to recover the reward, but instead it's just trying to imitate. So as at optimality, it outputs 0.5 uniformly across all states and actions. Now, why this 0.5 is because there is like at the optimality, the discriminator will be completely confused, and the discriminator is giving you a probability that this trajectory is coming from the expert or is coming from the generator. And then it reaches to 0.5, it means that I have no idea. There's like half chance that it's coming from the expert and there's half chance that it's coming from the generator. So at the optimality, this will happen, but what they want is a recovered reward as well. So they are proposing a specific type of discriminator that will also give you what was the reward function and what is the reward weights here. Okay. Now, as it progresses, they mentioned that our RL algorithm builds on the adversarial RL framework, which was proposed by Finn et al. Now, this Finn et al. Paper was the first time that, like the first paper that was talking about how we can mix the whole idea of GAN and adversarial, the GAN, so generative adversarial neural networks, and inverse reinforcement learning in order to find out what was the best reward function, what was the best policy here given the trajectory. So how can we use this whole idea of a discriminator and the generator, but to learn what was the reward and to learn what was the best policy here. Okay, so they, Finn et al., they propose a specific discriminator that would help to recover the reward. They have some arguments in this paper, in the AIRL paper, they have some arguments about this discriminator, and they mentioned that there are a bunch of problems with it, which we'll go through them very quickly. So they named the method proposed by Finn et al. As GAN-GCL, but yeah, so this is just some background that they are mentioning what are other works that are done here and like how they differ from their work. For example, this people, Amin et al., they consider learning reward functions which generalize to new tasks given multiple training tasks. So they say that our work instead focuses on how to achieve generalization within the standard IRL formulation. Now, what's the difference here? They say that these people consider learning reward functions which generalize to new tasks. Oh, so they want to generalize to new tasks given multiple training tasks, but they say generalization within the standard IRL formulation. So they probably don't have the standard IRL framework. All right. Now let's start to go through the background here. So as a background, let me go to my highlighting thing. So for the background, maybe, yeah, this one is better. They talk about that our inverse reinforcement learning method builds on the maximum causal entropy IRL framework, which was proposed by Szibart et al., which considers an entropy regularized Markov decision process defined by the tuple state, action, transition, reward, gamma, and rho zero. S and A are the state and action spaces, respectively. Gamma is between 0 and 1. This is the discount factor. And the dynamics or the transition distribution is this thing, and the initial state distribution is this rho 0 of S. And the reward function is unknown in the standard reinforcement learning setup and can only be queried through interactions with the MDP. Now, the goal of forward reinforcement learning is to find the optimal policy. So we have the forward reinforcement learning, and then we have the inverse reinforcement learning. So in forward reinforcement learning, we are trying to find the optimal policy that maximizes the expected entropy regularized discounted reward under pi transition and rho zero. So in forward reinforcement learning, we're going to find a policy, the best policy pi star, that would maximize the expected accumulated rewards. Now you can make it entropy regularized. So you are trying to regularize it by entropy. In order to just make sure that we are understanding what's going on and what's this H exactly doing, I'm going to use ChatGPT so that there's no missing information here. Because normally when we see regular reinforcement learning setups, we only have the expectation of accumulated rewards through times. But this type of entropy regularized case, this type normally comes in soft actor critic things or after like later policies that like later they were discovered, so they are not exactly compatible with like how the classic reinforcement learning talks about finding the best policy. So just in order to find out what exactly is H doing here and what's the goal of it, I'm just going to ask ChatGPT so that we skip reading a whole new paper just to understand what is the background here. Okay, so hold on, let me just go through the overlay first so we can get access to the formulation. Okay. What is H in this formulation, and give technical mathematics and background necessary. Use bullet points. Oops. Points to show clearly. Okay. Let's see. So based on what ChatGPT is mentioning, in this formulation, this H of pi refers to the entropy of the policy at a state S. It is a term that promotes exploration in reinforcement learning. Okay, so when you add the entropy, you're trying to promote the exploration in reinforcement learning by encouraging the policies that are not overly deterministic, thereby making the agent more likely to try different actions. Here's the technical background and mathematical details. Entropy in information theory. All right, hold on. Let me make this paper session here, and I'm going to add some text so that I can just put the background so that if I want to review it later, I know what to check. So this one is from the paper, and this is ChatGPT's answer on what is this age. Okay, let's read more. But let me just put these screenshots. This is like, I have to do these steps so that I know where to come back later. Okay. Oh. All right. Now, let's read. So we now realize that this is entropy, and this is in order to encourage the exploration. So encourage the policies that are not overly deterministic. So it is making the agent more likely to try different actions. The technical background and mathematical details. Entropy in information theory is a measure of uncertainty of randomness in a random variable X. Okay, so we know what is entropy. Entropy is like if you watch there's like a video talking about it in the Stacks, some YouTube channel. I'm not exactly sure what was the name, but it's like the funny YouTube channel that talks about these things in a very good language. So what they say is that it's like the inverse of the surprise that you will get from seeing some event. So it's like, imagine, let me just go through it maybe. Oops. Yeah, here. So it's like, imagine, normally in the binary thing, when they talk about entropy, they specify this table. So it is like when it's 0.5, when it is 0, and when it is 1. And this is like a probability, the binary probability. Normally, the entropy goes through like this. So it is like when it is in the 0, you are 100% sure that this event is not going to happen. So the entropy is on its lowest form. When it is in 1, you are 100% sure that this event is going to happen. So the event is on its, so the entropy is on its lowest form. When you're in 0.5, you are completely unsure that this event is going to happen or it's not going to happen. So the entropy is on its highest level. So it's like it has the highest entropy ever. So that's why we have this entropy in information theory, which is a measure of uncertainty or randomness in a random variable X for a discrete random variable with probability distribution of px, and the entropy is defined as the negative of p log p. In reinforcement learning, entropy is used to encourage exploration by promoting stochasticity in the policy. So it is trying to promote stochasticity in the policy, and this way it is encouraging exploration through that policy. The idea is that the higher the entropy means a less deterministic policy, encouraging the agent to explore a wider range of actions. So here, when we say that we're trying to find a policy that would maximize this, we are kind of maximizing the entropy as well in the formula. So it is like a mixture of both maximizing the accumulated reward and having a high entropy, meaning that we are trying to high up the exploration here. Okay, I need a 5-minute break. I'll come back so that we can go through the other part of the reading here. So yeah, just have a 5-minute break. I'll come back very soon. Okay, I'm back again. Oops, I hope that wasn't so loud. All right, let me set the timer again and we can go through it. So where were we? In the ChatGPT's response. All right, so as you were saying, the idea is that the higher entropy means a less deterministic policy, encouraging the agent to explore a wider range of actions. Okay. Now, policy entropy. How do we define the policy entropy? So because the policy itself is a probability, we can just put it directly there. So for a policy that defines the probability of taking action A, given a state S, the entropy at a state S is just the negative of summing over all of the actions of the pi times log pi in that specific state. This entropy term is added to the reward to encourage the agent to explore various actions rather than always choosing the same one. So in order to encourage exploring different actions, i.e. just the exploration basically, we are adding this entropy term so that the policy has to explore different actions. Okay. All right. Now, as the next thing, it mentions that entropy regularized reinforcement learning. In traditional reinforcement learning, the goal is to maximize the expected cumulative reward. So we're in traditional reinforcement learning, we're trying to maximize this thing, as I mentioned. However, entropy regularized RL modifies this by adding the entropy term to the reward, leading to a new objective. So now we are trying to maximize accumulated reward, but still, we are also trying to maximize the entropy as well. Including this edge makes the agent favor exploration during learning, which can improve the performance in complex or high variance environments by avoiding local optima. The discount factor is just, we know what is discount factor. It controls how much the future reward matters to us, and the entropy are valued compared to immediate ones. Oh, and as you can see here, I didn't notice this, but the discount of a factor is also multiplied, like this parentheses starts here and ends here, so the entropy is also discounted. A higher gamma values long-term exploration and rewards, while a lower gamma prioritizes immediate rewards. And next we have the expected trajectory, which is just the expectation over the trajectories. This tau represents a trajectory or a sequence of states and actions. This expectation denotes the expected value of the sum over all possible trajectories, weighted by their probabilities under policy pi and the transition dynamics tau. Okay, so now we know what exactly this H means. Let's keep on. So in the forward reinforcement learning, the goal is to find this policy that will maximize this expression, where tau is just a trajectory, a sequence of states and actions induced by the policy and dynamics. It can be shown that the trajectory distribution included by the optimal policy pi star takes the form pi star, which is, so the pi star, now if you want to find the optimal policy, this optimal policy is proportional to the Q star, soft Q star of ST and AT. So the best policy is proportional by e to the power of Q, a star, but the soft Q. It is shown in Zibart's thesis as well as this Harnoja thing, which I think it's the SAC paper, even though I'm not completely sure, where this Q star soft is basically R plus the expectation over accumulated rewards for the next state and the entropy. Okay, denotes the soft Q function. Inverse reinforcement learning instead seeks, now this was whole about forward reinforcement learning. Now, inverse reinforcement learning instead seeks to infer the reward function given a set of demonstrations. In IRL, we assume that demonstrations are drawn from an optimal policy. So we assume that the demonstrations are drawn from an optimal policy pi star. We can interpret the IRL problem as solving the maximum likelihood problem. So we're trying to find the thetas that would maximize the likelihood of getting a trajectory from some demonstrations, but we're trying to maximize the log likelihood of it. So it is the log of the probability of that theta coming from that trajectory. So where this p theta is proportional to p of s0 times the probability of going to other states, while we are trying to multiply it by this exponential of gamma r theta. This parameterizes the reward function, but fixes the dynamics and initial state distribution to that of the MDP. Under deterministic dynamics, this simplifies to an energy-based model. Therefore, feasible trajectories, we have that p theta of that trajectory is just proportional to e to the power of the summation over all the rewards. Okay? So, yes, I guess it's all okay. Now, Finn et al., they propose to cast optimization of equation 1 as a GAN, so we can make it a GAN optimization problem. They operate in a trajectory-centric formulation. So the difference here is that they provide a trajectory-centric formulation, which later they mentioned that using the trajectories as a whole would not be a good idea probably, so they switched to a state and action, the authors of this paper. So where the discriminator takes on a particular form, this is the form of the discriminator. F theta is a learned function, pi theta is pre-computed, and its value is filled in. Okay, now let me maybe highlight the discriminator here for yourself. Okay, so the discriminator that Finn et al. Mentioned is such that we have an exponential of this f theta, which is, we can assume that it's like the reward function or the reward network. So an exponential of the reward network over the trajectories divided by the exponential of the reward network over the trajectories plus the policy of the trajectories. And this policy is basically the generator function. So this is the generator. This is the discriminator. And this one is the reward network or reward function. Okay, so the whole idea is that on a trajectory, e to the power of, it's like a summation over all of these states and actions of that specific trajectory of the reward functions divided by e to the power of this summation of the reward functions plus the generator probability would give you the discriminator thing. The policy pi is trained to maximize this expression. So the generator, the policy pi, is trying to maximize this expression. So the generator's goal is to make the discriminator fool me for the expert. How? It is trying to maximize this specific reward. That's expression is just 1 minus theta. So it's like it's the same as the loss function for the GAN. So if the discriminator does a good job, if the discriminator tries to specify the trajectory as the expert in the correct way, the generator will get a negative reward. But if the discriminator does a bad job, like if it confuses the trajectory that is generated by the policy as a expert trajectory, this reward will become higher. But just to make sure, let's also ask this from ChatGPT to maybe give us an explanation of what's going on here, so we don't miss a thing. All right. Explain what is the policy trained on? How is the reward function of the policy helpful? And also explain how the discriminator work. Use bullet points and make it here. Okay. All right, here's the breakdown of how the policy is trained, the role of the reward function, and the functioning of the discriminator in the scan-based framework for IRL. Policy training is trained in an adversarial setup where it interacts with a discriminator D that distinguishes between expert and non-expert behavior. Training the policy involves maximizing a reward signal derived from the discriminator's output, guiding the policy to produce trajectories similar to expert demonstrations. The policy is optimized to fool the discriminator, making it difficult for the discriminator to distinguish between the trajectories generated by the policy and those by the expert. Okay. Reward function for the policy. The reward function for the policy is given by this r tau, which is equal to the logarithm of 1 minus theta minus log of theta. Okay, so this is the reward. The reward function is a structure to assign higher rewards to trajectories that the discriminator... Okay, hold on. Maybe an example would be a good thing. Can example of how the reward works. Okay, so the reward function is a structure to assign higher rewards to trajectories that the discriminator finds difficult to classify as non-expert. The more expert-like a trajectory appears, the higher the reward. By maximizing this reward, the policy is incentivized to generate trajectories that closely resemble the expert's behavior. I see. The discriminator d theta in the GAN framework. The discriminator serves as a binary classifier in the GAN framework, distinguishing between trajectories tau generated by the expert and those generated by the policy. The form of the discriminator is this thing that we went through, where f theta is a learned function that evaluates how likely a trajectory is to be an expert trajectory. And pi tau is pre-computed probability assigned by the policy. The discriminator outputs a probability value indicating how likely a trajectory is to be an expert trajectory versus a generated one. Discriminator training process, trained to output high values, blah, blah, blah. Okay, I think this doesn't matter that much, but let's go through this thing. Okay, so a reward calculation for the policy. We said that this RT is coming from the log 1 minus d theta over the trajectory minus log of t theta tau. So it's, as an example, it says like if the discriminator thinks that the trajectory is non-expert. So for example, this d theta will give you a very small value, close to 0. So it is assuming that it is non-expert-like, okay? In that case, the reward will be larger. Why? Because this value will have a positive thing. Okay, however, if the discriminator finds the trajectory highly expert-like, so it is like 0.9 expert-like, then this r tau will be smaller because this log will contribute more. Log 1 minus d theta will contribute less. Okay, as an example, like it's assume this theta is equal to 0.1. The log of this expression will be somewhere around 0.9. However, if it assumes that it is coming from the expert, the reward will be... What happened here exactly? Okay, let's see. Expert-like trajectories, at which point the reward... maybe ChatGPT is making a mistake here, but let's see. What if the non-expert like trajectories yield a higher reward? Wouldn't the policy be motivated to make more of them? The reward function for the policy is actually to expert-like but non-expert ones. Let's clarify. When the policy produces clearly non-expert trajectories, the discriminant can classify them as non-expert. This theta would be 0. So if it is 0, this will be like negative infinity. Oh, I see. Okay, I think this has made a mistake here. Yes, it has made a mistake. I think this is not correct calculation that we got here. Let me just make sure about it. Yes. Hold on, let's see. 1 minus. And then we have this expression. Okay, what if we have 0.5? Okay, what if we have like 0, 1? 0, 1. Okay, and on the next step we'll have like 99. 99. What about this case? Okay, 99. Oops. This one versus the case where the discriminator is pretty sure about what's going on. So it's like 0, 0, 0, 0, 0, 1. I don't exactly see what's happening here. Oh. -0 minus log 0. But this is giving us a positive value. When theta is close to 0, oh, I see. Oops. GAN discriminator loss. I think what's going on here is that we are trying to make this discriminator to be as close as possible to 0. The output of the discriminator to be as close as possible to 0.5. So it's like half the way through. And anything other than that has to be... Okay, now the problem here that I still don't understand is how can we tell... Now, I see that if the discriminator outputs 0.5, meaning that it is completely confused of what's going on, we will get a reward of 0. But the problem that I have here is that if we have a discriminator that is outputting higher values, except for the fact that it cannot reach, I think it cannot reach close to 1 thinks. Okay, hold on. Maybe I'll make a new chat. What is the discriminator? Oops, discriminator of GAN's output range. Zero to 1. So presents the probability. A value close to 1 indicates that believes that the is highly likely real. A value that is close to 0 indicates that how is this idea used in GAN IRL? So in GAN-based inverse reinforcement learning, the discriminator plays a role. Output is still where values close to 1 suggests that this is from the expert, and values close to 0 suggests that it's from the agent's policy. Okay, can you give a numeric example of the reward function of the generator policy and how it is pushing the policy to make more expert-like dreads. All right, let's see. So just saying, like, there's a bunch of demonstration, etc., etc. So it says if the discriminator is close to 1, the pair is likely from the expert, and if it is close to 0, it is most likely from the agent. Oh, now here the reward is just log of the essay. But isn't the reward log of the log of 1 minus the minus log of the? Now, is the policy trying to maximize this reward or minimize it? Alright, in GAN-based IRL, the agent's policy is trying to maximize this reward. Oh, the reward is higher when discriminator is uncertain, which is closer to 0.5, meaning that it can easily tell if the state action pair is coming from the. If D is close to 1, R becomes negative. If D is close to 0, R becomes positive. I don't get it. I think I need to ask it from someone. Maybe let's have a little break. I'll come back in like 10 minutes, but I have to understand this thing before moving forward. Okay. So for now, I'm just gonna stop the stream here, and we'll come back when I have a better answer about what's exactly happening in this thing. So hold on. Yeah, maybe I'll see you in like 15 minutes or so, but we can continue this paper